So in this video, we're going to talk about the ideas of boundedness and monotonicity for sequences. Fun words to say, or monotonic is anyways. So a sequence is called bounded from above if there is a number n such that a sub n is less than or equal to m for all n. So we call m an upper bound. And then we can say that if no number less than m is an upper bound, then we call m the least upper bound. Okay, so this is kind of a dense idea, so I think it would be a lot easier if we just did this with a sequence. So let's say I have the sequence a sub n equals 2 minus n. Okay, so my sequence starts at n equals 1. So if I were to just compute a few terms of this sequence, it would be 1, 0, -1, -2, so on and so forth. Okay, so the thing is that we say that this sequence has an upper bound. So these are numbers, so just remember, your sequence cannot exceed that number. It has to be less than or equal to that number. So all of the terms in this sequence would be less than, I could just start shouting out numbers here, 3, 7, right? The sequence is definitely going to be less than 3, 7, really any other number less than or equal to 1, right? Which means that the fact that I know that this sequence is just going to keep decreasing, 1 is the least upper bound. Because again, the idea is that your sequence has to be less than or equal to that number. So the biggest that this sequence will ever be is the 1. And then otherwise, anything above 1 is also an upper bound, but 1 is the least upper bound. So that's the idea behind that. Now, analogously, we also have the idea of being bounded from below. So a sequence is bounded from below if there was a number m such that a sub n is greater than or equal to m for all n. So in this case, we call m a lower bound. And so if no number less than m is a lower bound, then it will be called the greatest lower bound. So it's a very similar idea to the upper bound. So in the event that a sequence A is bounded from above and below, then we call that sequence bounded. So if a sequence is not bounded, then it is unbounded. Okay, so now let's just think about this for a second. So I'll give you a moment to think about it. I would see if you can write down an example of this before I tell you. What is an example of a sequence with a lower bound but no upper bound? So maybe pause for a second, write something down, and then hit play when you think you've got it. So there's a lot of different sequences that have a lower bound but no upper bound. So a lower bound, so that would be a number from below, right? These are sequences that just keep getting bigger and bigger. So just a sequence as simple as 1, 2, 3, 4, 5. So in this case, 1 would be the greatest lower bound, right? This sequence will never go lower than that. Or you could have something like 2, 4, 6, 8, 10. In this case, 2 would be the greatest lower bound. Okay, so now what about a sequence with an upper bound but no lower bound? So again, maybe you want to just think about that, and you could pause here if you wanted to and write one down. Okay, so we actually already saw a sequence with an upper bound but no lower bound, but I thought of two others. So really common ones that come to mind are things with like fractions. So in this case, if I start with 1, then 1/2, 1/3, 1/4. So obviously the largest number in this case will be 1, and everything is kind of going below that. So this would be the least upper bound, or you could have 1, 1/2, 1/4, 1/8, so on and so forth. So both of these would work. If you had anything kind of with that idea of there is the largest number that you're going to get to and everything else is going to decrease after that, then you're good to go with this. Okay, so now what about a bounded sequence that does not converge? Okay, so can you think of something like that that might work? Again, maybe pause for a second, write down a guess or two. So a bounded sequence that does not converge. A really classic example of this would actually be the sequence 1, -1, 1, -1. So just bouncing back and forth between 1 and -1. The sequence is clearly bounded both above and below. So it's bounded above by 1 and below by -1, but it just keeps bouncing back and forth. So it's never going to have a clear value that it converges to. So this is a really common sequence to use when we're talking about problematic sequences that don't do what we want. Okay, so next, let's talk about the ideas of non-decreasing and non-increasing. So a sequence is called non-decreasing. This always like messes with my head, but a sequence is called non-decreasing if a sub n is less than or equal to a sub n plus 1 for all n. And then we call it non-increasing if a sub n is greater than or equal to a sub n plus 1 for all n. Okay, so just to wrap your head around what does this even mean, let's just start with two sequences here. So I've got 1, 2, 3, 4, and 5, and then 1, 1/2, 1/3, 1/4, 1/5. Okay, so between these two, which is non-decreasing versus non-increasing? You can pause if you want to think about that for a sec. So this first one would be an example of non-decreasing, right? So each term before the next term is smaller. So that's the whole thing, right? A sub n is less than a sub n plus 1. So this is the whole idea. So yes, each term is smaller than the next term. Versus non-increasing, so remember the idea behind this is that a sub n is greater than or equal to a sub n plus 1. So each term here is bigger than the next term, so that's non-increasing. Okay, so that's the difference between those two. And so we call a sequence monotonic if it's either non-increasing or non-decreasing. So if it's not one of those things, then it is non-monotonic. So what would be a classic non-monotonic sequence? Again, that would be our 1, -1, 1, -1, because it's just bouncing back and forth. So this is non-monotonic, and it's also unbounded. Or it actually, no, it's bounded, but it's non-monotonic. Sorry, my bad. Okay, so the last thing that I want to talk about is called the monotonic sequence theorem. So this says that the sequence a sub n, if the sequence a sub n is both bounded and monotonic, then the sequence converges. So this is a really handy thing to note. If you have a sequence that you can figure out as bounded and monotonic, then boom, you know it converges by this theorem. Okay, so this video was just a short and sweet one, so I'm going to leave it at that, and I will talk to you guys in another video. Bye!